Hello everyone, welcome to the first week of Mat223. Today we'll be talking about system of linear equations. So first of all, let's take a look at the definition of system of equations. An equation is called linear if it has the form of a1x1 plus a2x2 plus all the way to an xn equals to k. So notice that for a's right here, these are what we called coefficients. And for the x's right here, these are what we called unknowns or variables. And at last, for the k on the right-hand side right here, this is what we called a constant. And for our constant term right here, it has to be within the real number system. So that is the case for having one linear equation. What if you have more than one linear equation? In that case, you'll be having a system of linear equations. A system of linear equations is a finite collection of linear equations using some or all of x1, x2, all the way to xn's, as in these equations right here. So it has a general form of this. A system of m equations with n unknowns can also be referred to an m by n system. So notice that for this expression right here, the row always comes first and the column always comes last. So let's take a look at example 1. Example 1. Is this equation linear or nonlinear? Explain. So let's take a look at this equation. We have 3x1 minus 4x2 plus 7 square root of x3 equals to 5. So what do you guys think? So first of all, we can say that we have coefficients 3 minus 4 and 7. And we also have a constant term here, which is 5. Now, our variables right here has x1, x2, and square root of x3. Notice that for linear equations, our variables will be having the power of 1 only. So if you're not sure about that, we can always go back to the definition right above this example, and we can see that for all of the variables here, the power has to be 1. However, for our x3 variable right here, it has a square root attached to it, which means the power here does not equal to 1. And in fact, the power equals to 1/2. So because of this equation is not linear. Now, let's take a look at the solutions to a system. A solution to a system is a solution to every equation of the system. That means it must satisfy every equation in this system. So first of all, if a system of equation has at least one solution, then it is called a consistent solution. Well, notice that there's actually 2 different cases when considering a consistent solution. So the first case is when you have unique solution. And the second case is when you have infinitely many solutions. So I'll talk about that a bit later in the section below. Secondly, if a system of equation has no solutions, then it is called an inconsistent solution. So a recap, consistent, it might be a unique solution or infinitely many solutions. Inconsistent solution, it's straightly linked to no solutions. So now let's take a look at example 2. Determine if the following system of linear equations are consistent or inconsistent. So let's take a look at case 1. Case 1 right here, we have x plus y equals to 3 and x minus y equals to 1. Let's define these two equations. Let's call the first one as equation 1, and let's call the second one as equation 2. We can use subtraction, which is equation 1 subtracting equation 2 to get the values for y. So in this case, we'll be having x plus y minus x minus y equals to 3 minus 1. And that will give us 2y equals to 2, meaning that y equals to 1. And if you sub y equals to 1 back into any of these two equations, then you'll be getting x equals to 2. So this gives us a unique solution because this set of value is unique to this system. So for case 1 right here, the system is consistent. Now, let's take a look at example 2, case 2 right here. Again, we have two equations, x plus y equals to 3 and x plus y equals to 1. However, if you take a very close look at these two equations, you will see that on the left-hand side, they're both x plus y's. However, on the right-hand side, one equation is telling you that x plus y equals to 3, and the other equation is telling you that x plus y equals to 1. So if I write it horizontally, this means x plus y equals to 3 equals to 1. And this does not make sense intuitively. Even if you haven't learned any linear algebra in this course, you will still know that this would not make sense because 3 cannot be equal to 1 at the same time. So simply saying for this system right here, we cannot find any value for x and y's that satisfy the system. That means that there is no solutions. Hence, this system is inconsistent. Moving on, let's take a look at system as augmented matrices. So in the previous session, we talked about a system of linear equations. Now, what if we put a system of linear equations into a matrix? More specifically, that matrix will be called an augmented matrix, simply because it has this bar right here. So whenever you have a matrix that has a bar to separate the coefficients and the constant term, then this will be what we called an augmented matrix. So the only difference between a system of linear equations and an augmented matrix is that for a system of linear equations, we have both the coefficients and the variables sticking together. Right? However, for the augmented matrix, we simply put the coefficients on the very left side to the bar, while we put the constant terms on the right side to the bar. So you might be wondering, where did the coefficients? So you might be wondering, where did the variables go? the variables are actually represented by each column. So for the first column, as we can see, the first column are all x1s. So actually, there's a hidden x1 right here. For the second column, it's all x2s. So for this corresponding column, this is for x2s, so on and so on. So for the last column here, this is for xn. So notice that for an augmented matrix here, you don't put the variables or unknowns in the matrix. Moving on, let's talk about elementary row operations on a matrix. Elementary row operations help us to simplify any matrices. So it has three main rules. The first rule that it has is that it allows us to interchange two rows. That means you can either swap row 1 with any other rows. It can be row 2, row 3, depending on how many rows your matrix has. The second rule here allows you to multiply one row by a non-zero number. So that means you can multiply, say for example, row 3 by k, where k does not equal to 0. Notice that when you're multiplying row 3 by k like that, you're operating row 3. So you don't multiply k by row 3 and put that row on row 2. And I'll explain more about that later. The third rule allows us to add a multiple of one row to another row. That means that, say for example, if I'm operating row 3 again, right, I can add or subtract, because subtraction is just another form of addition, right? So I can add or subtract another row to row 3 when I'm operating row 3 again. All right, so after talking about the rules for elementary row operations, let's take a look at example 3. So in example 3, we have to perform row operations to the following matrix. So as we can see for this matrix right here, it has the first row as 1 minus 1 minus 1, 4. For the second row and third row, it has 2 and 3 as the first term. When you're doing row operations or row reduction, one thing that you always want to do is to get rid of the terms under a leading one. Which is this one, highlighted in blue. And the reason why you want to do this is because you would like to simplify the matrix. So what we can do here to this matrix is that for the first step, we can use row 2 minus 2 row 1 to get rid of the 2. And we can do the same thing for row 3. So instead of subtracting 2 row 1 for row 3, because our first term is 3, so we subtract 3 row 1. And that will give us the following matrix. So now take a look at row 2 and row 3 in our new matrix. They look very similar, right? Except for the -7 and -13. So what we can do here, we can make it simpler again by using row 3 minus row 2. In this case, the new matrix that we get will be having the same row 2. However, for row 3, on the coefficient matrix side, it will be all zeros. And on the right-hand side, which is the constant term side, this will be resulting in a -6. And we can do one more thing to further simplify the matrix itself. So say, for example, for row 3 right here, we can divide it by -6 to make it look simpler. And for row 2, we can divide it by 3 because of this 3 right here. And the reason behind is that we want to make another leading one. Okay, so now we have this matrix. So if I'm asking you this question, is this final matrix consistent or inconsistent? And what would you say? So let's take a look at the last row of the matrix here. This last row here is basically saying that 0 multiplying x1 plus 0 multiplying x2 plus 0 multiplying x3 equals to 1. I'll give you guys a few seconds. Ask yourself if this is possible or not. And I'm pretty sure the answer is no, because 0 multiply everything, anything, will be 0. And now this equation at the very last row is basically telling us that no, 0 multiplying something can result in 1. So you can't find any number for x1, x2, and x3 to satisfy the system. So for the entire system right here, circled in green, this is actually an inconsistent system. And if I'm asking you one more thing about this example, for this form right here, is this the most reduced form, which is called the RREF form, or is this just the REF form? So if you're wondering what RREF and REFs are, I'll be explaining those in the next page or the next session.